Okay, this next demonstration that I'm going to look at was generated by something called Null Geodesics in a Schwarzschild Metric. This circle here represents the Schwarzschild metric, or the Schwarzschild radius of a black hole. This is the point where light falling into the black hole basically comes to a stop from the perspective of the outside world. While this was a very carefully chosen vector where it's coming in so that it's crosses the tangent line at the top, and it's just at a certain direction where the actual light can go into orbit around could go into orbit around the black hole. Now the ones that are just a tiny hair fraction above that tend to spray out into space after looping once, and the ones that are just a tiny bit below that end up falling into the black hole. Now the Schwarzschild metric can be found on Wikipedia if you see this equation here. So let's see what assumptions that I applied in doing this demonstration. One, since I'm working with the null, I pointed out the null geodesic in the Schwarzschild metric means that the amount of time actually experienced by a photon is 0. So that means that this part becomes 0 equals, and then the rest comes down. And secondly, a second assumption I made was theta equals pi over 2. So basically, if you imagine a sphere and the far point on the sphere would be theta equals pi, the near point on the sphere, the line vector pointed towards us, would be theta equals 0. So around the edges would be theta equals pi over 2. So I'll plug in theta equals pi over 2, which means d theta equals 0, and sine squared of theta equals 1. So that means we can cross this out, and we'll just move this down, and we'll have minus r squared d phi squared. And all of that is equal to 0. Now at this point, I'm having a little bit of difficulty remembering precisely what I did. I remember specifically that I was mostly concerned with this difference between d phi and dr. And I keep very bad notes, except for the fact that I still have the code. And here's a primary part of the code. The next status function here. Now let's try this out. I'm going to run this, and if I remember correctly, what this usage thing does is when I put question mark next status, hold on. So if I type in question mark next status, it will actually tell me what that code does. It says next status. It takes the inputs x, y, theta, w, and t, takes a position x, y, and a direction theta, and creates 2 photons, a distance w apart, centered at x, y. So you give it a position and a direction. You basically just give it a position and a direction, and then it gives you two photons, distance w apart, centered at x, y. Then the velocities and positions of these 2 photons are calculated. Of course, the velocity of the photon is entirely I think it's determined by this relationship here. This relationship gives us, well, you give it, I guess you give it any two variables of r, phi, and t, and it will give you the third one. So if I know the direction of the photon, then I know dr d phi. What this can give us is the dt, which would give us both dr dt, which is the radial velocity, and the d phi dt, which is the radial velocity. And if you take r d phi dt, that gives you the tangential velocity. So it looks like even while I was writing this code, I still had some questions about this. For instance, it says the space-time interval between x comma y and x final y final may not be 0, but really that's you don't have space-time intervals between positions. You would have basically you would have x, y, and t at that, when the moment where the photon passed that point, and x2, y2, t2, the moment in space and time where the photon passes that point. And the idea here that the space-time interval, which is basically this d tau, the d tau is the space-time interval, and that should be 0 for a photon. There is no basically, as far as the photon is concerned, we need to find a route through those positions and times so that this quantity evaluates to 0 for the entire path. So that might be a thought regarding something that this is not for light, but maybe I was thinking of possible ways to implement things besides light falling into the black hole. If we define this as something other than 0, then that's not light. It's would have to be a particle of some kind. Let's look at this. Another thought. A straight space-time interval might not be 0, but is the curved space-time interval 0? And looking back at that now, I would say, of course not, and of course not, and of course. And that's basically the whole concept of what's going on in this animation, is that all of the motion of all of these photons that are going around these curves, the space-time interval between those, between the events, the event here where the photon starts to enter and the event here where it falls into the black hole, the space-time interval is 0, which is the amount of time that the photon would actually experience during this phenomenon. Essentially, even though we see the photon going around in loop-de-loops, from the perspective of the photon itself, all there is whatever happened at the back end of this. There's just two events associated with the photon, which is the emission and the absorption. To the photon, there is no other event. It's just an interaction between the emission location and the absorption location. But for us who live out here in the world of stationary objects, the photon is appearing to move in circles and around curves and stuff like that. So basically what the Schwarzschild metric is doing, it's giving us the relationship between these four variables. Coordinate time, which is basically what I'm using in the animation as our time variable. Radius, which is the distance from the center of the circle. and this phi, which is the angle going around the circle that goes 0 to 2 pi. Now, you'll see the first thing I defined in this code is f of r, and the reason I did that was, you will see right here, this, not this one actually, but this one. This is the coefficient before the time variable. And we can see that being used here in calculating the tangential velocity. Now, I find that this is a pretty long piece of code, so I'm not going to try to explain every detail of it before I go. But the main concept I had was, we have a photon coming around the circle. And what I did was I split this photon into two parts, or I found a little bit above the photon and a little bit below the photon. And given the value of r and phi, because phi goes from, well, say this is 0 all the way back around to 2 pi, given the value of how far it was and how far the angle was, I calculated, basically find the radial velocity, which was v radial would have been dr dt, and the tangential velocity, which is r d phi dt. And then from those two velocities, and well, those two velocities were really pretty well determined by this equation. If I give it dr d phi, you can solve for dt, which gives you the radial and tangential. So in any case, if I had those two velocities, these would be different. These two velocities would be different, and therefore by just slowing one of them down, I could find a kind of a new direction based on those two velocities. Which, because if the wheels on the right side of the car are slower, that makes the car turn, and I basically just used that new vector based on how far they turned. But that required me to find an incline, which was basically the radial over the tangential velocity. And then based on that incline, I could find a new tangential velocity. Based on that incline, I could find a new tangential velocity and a new radial velocity. And then I converted that back into Cartesian coordinates, the x and y coordinates. But I did that twice, one based on x plus x component 1, y plus y component 1, and one based on x minus x component 1, y minus y component 1. These two points were based on the current direction, I guess, of the current direction that the photon was traveling, and basically rotating that direction by 90 degrees and adding width over 2. So this was finding how far apart locations of the two sides of the photon. So the two sides of the photon was x2, y2, and x1, y1. Then we calculated the two velocities of those two sides of the photon. Then we calculated two new positions based on those two new velocity, on those two new velocities. And then we took the average of those two new velocities to find the average position of the photon. Now, the new direction of the photon is determined by x component 1, x component 2, or x component 2, y component 2, and x component 2, y component 2 is basically determined by the old position, the new position, and old position of the photon. So what is returned is that new position of the photon and that new direction of the photon, which is based on the initial and final positions of the photon. So to be clear, this demonstration is using tiny increments of time, and really what it's doing is replacing these differential things with tiny delta r's, tiny delta ph's, and tiny delta t's, and setting this d tau equal to 0. So depending on how small, if my delta t's, delta r's, and delta ph's are not small enough, then we may end up with flaws in the may end up with small inaccuracies in the diagram itself. Here's an earlier version of this that I think may have had this problem. You'll see in a few places on here a photon kind of pops through the and that may be because of an incremental change where the velocity in the previous calculation was sufficient for it to actually bust through the event horizon, but in fact it would have gone to 0 before it. The velocity should have gone to 0 before it hit the event horizon. And I wanted to point out another aspect of this, was that in some of these demonstrations, and I'm not sure which is which, but I applied this coefficient to dr squared, and in some of them I didn't, and the difference between using it and not using it was not a real substantial thing, but you can see it right here. You'll see that the photons are actually moving a little bit faster towards the thing, the ones that are coming straight in, than the ones that are going around. So anyway, let's compare this, what happens depending on whether I leave this term out of the demonstration or leave it in. There is actually a pretty observable effect depending on whether I leave that in or not. Here is the non-Schwarzschild version of it. This is where we leave out that extra term. And here is the regular Schwarzschild version where you leave in that extra term. And the difference is that this goes all the way around, and this one appears to only make it about 3/4 of the way around. And that kind of goes along with the with Einstein's 1916 measurement, I guess, or maybe I don't remember exactly when it was, but the deflection of photons around the sun during a solar eclipse seemed to be about twice as much as he expected, basically because they were expecting this much deflection based on only this term being there, but they ended up with a greater amount of deflection because both of those terms should be up there. Now I have seen a derivation of this part of the thing that I can make sense of. I have not actually seen a derivation of this part that I can make sense of. So I can say that understanding what's called Einstein field equations and how this becomes a specific solutions to it is something that I would like to do in my following years. That is, whether I learn it over the next few weeks or the next few months or the next few years, I would eventually like to understand precisely how this term gets in there. Perhaps in shortly I will describe how this term can be got in there basically from that elevator experiment in my last video, there's a way to get this out of that elevator idea.